So in this video I'm going to introduce the formal theory of integral calculus of integration. Now there are two major ways to formally define integration, and they are called the Riemann integral, Riemann integration, and the Lebesgue integral, Lebesgue integration. Now of those two ways, the Riemann integral is far more simple. And it's the one that is usually taught on the first course in real analysis, and it's the one that we're going to look at in this video. We're not going to talk about the Lebesgue integral at all, that's much more advanced. Now, within the topic of the Riemann integral, there are multiple different ways that you can actually define the Riemann integral. They're all utterly equivalent to one another, and they're all demonstrably equivalent to one another. We are going to look at a definition of the Riemann integral that is called the Darboux definition of the Riemann integral, because it was concocted initially by the mathematician Darboux. So this way of defining the Riemann integral is actually different to the way that Riemann initially actually came up with. The reason I'm going to do that is because the way that Riemann initially defined the Riemann integral, although very intuitive, is actually extremely difficult to prove anything with. It's tricky to work with, whereas the Darboux definition of the Riemann integral is much more easy to actually work with. Proving a lot of the theorems that we want to prove about integrals follows very simply when we use the Darboux definition of the Riemann integral. So that's the one that I'm going to introduce you to in this video. So let's now have a look at this definition then. So we will have a function which we'll call f, which is going to be defined on the domain, which is a closed interval from a to b within the real line, and it's going to be, of course, a real valued function. And now what we want to define is what is meant by this, the integral from a to b of f of x dx. What does it mean for this function to be integrable? And because we're looking at the Riemann integration definition, we will say, what does it mean for this function to be Riemann integrable over this interval from a to b? What is this defined to be? Now, this is an analysis video, so you've all presumably studied calculus, so you know what we want it to be. We want it to mean, intuitively, the area under the curve. So if we plot a little picture here of our function, so here's our interval that it's defined on, the interval AB, and then graphically the function might, let's say for the sake of argument, look something like this. And then intuitively what we want this thing to capture is this area under the curve, so all of this. So how are we going to do that? How are we going to formally define this? Well, one thing that might come to mind for how you could go about formally defining this, if you sit down and try and do this for yourself, you might go to calculus, because after all, that's what we're trying to build, and you know something very powerful about how to do this. You know that if you have another function, which we usually call capital F, that differentiates to little f, then that's extremely helpful in finding this integral. So if we have a function capital F defined on this interval AB, which again is a real valued function, such that if you take the derivative of capital F at every point, it's equal to the function little f. So we'll need this function to be differentiable everywhere over this domain, and then if it gives the values of this function everywhere, then we can call it the antiderivative of little f. So little f is its derivative, and it is the antiderivative of little f. Then we know from calculus that this area under the curve is actually equal to capital F evaluated at B minus capital F evaluated at A. So having an antiderivative is extremely helpful for finding this. So one of the ways we could formally define this, it's a little bit of a disappointing way, but it is a way we could proceed, is we could just define it like so. We could say, if your function little f has an antiderivative big F, then we will just formally define this thing to equal big F evaluated at B minus big F evaluated at A. What I would then have to do is demonstrate to you how this actually does capture the concept of the area under the curve which we could do, but there's nothing wrong with that formal definition. That is a very formal, precise definition for how I could define this. The reason we don't do it like this is because it relies on us being able to find this function capital F for little f, and that puts a limit, not a formal limit, I'm just using the word limit as in the English word limit. That puts a constraint, introduces problems. It means that there are functions that we would like to be able to define the integral for where it's going to be very difficult, and let me give you an example. So a very famous function from statistics, and also actually analysis, it's a very important function, is the function e to the negative x squared. So if you've done any statistics at all, you should know what this function is. It's a bell-shaped curve. It's the Gaussian function. So it looks like this. Now, it's very related to the normal distribution. This one isn't actually quite a normal distribution because it's not standardized. If you integrate it from negative infinity to infinity, it doesn't equal 1, this one, so it needs some constant out the front to correct it. But ignoring that, this is the normal distribution curve. Very, very important in statistics because no matter what random variable you take, well, actually there are a few constraints. The random variable needs to have finite mean and finite variance, but as long as those two things are met, then no matter what random variable you take, it can be something absolutely crazy. So it could be distributed, for instance, and this is just a little bit of a sidetrack. This isn't important to our discussion of integration, but this is just an interesting part of maths. So maybe it could be distributed like that or something absolutely crazy, some hideous distribution. If you sample from that random variable and compute a statistic from your sample, so let's say you take a sample of size little n, where little n is some positive integer, and they're picked randomly according to this probability distribution here, then if you compute a statistic from your sample, say for instance you compute the means of the values you get, which we might call x bar, that's an example of a statistic. A statistic is just a number that you compute from a sample. In fact, we can even call it a sample statistic if we want to be very precise. Then the reality is if you take different samples, so if I take a sample of size n and then I get another person to take another sample of size n and a third person to take another sample from this probability distribution of size n, we're all going to get different values for the mean because our samples are all going to probably be different. So you can then ask the question, well, what is the probability of getting a certain value for that sample mean when you take a simple random sample from your original probability distribution? So there's another probability distribution for the probability that you get a certain value of the sample statistic, and that's called a sampling distribution. And there is an incredible theorem, incredible analytical theorem in probability called the central limit theorem that says that the distribution of a sample statistic, of the sample mean, is going to be normally distributed approximately. And indeed, as you make the sample bigger and bigger, if n tends to infinity, it truly converges on being normally distributed in this fashion, around the mean of the actual original probability distribution. So if this is our real distribution, then maybe its mean is here, and we'll call that mu. Then the sampling distribution is actually going to be normally distributed around mu. So this is the sampling distribution for what values you're likely to get of x bar. And as you make n bigger and bigger, it becomes more and more closely to being normally distributed. And in fact, the variance of it gets smaller and smaller, so it becomes really sort of centered around that mean, so that your chance of getting anything above or below becomes lower and lower. I've drawn that slightly badly because it shouldn't be like that. It should be, I've made a complete mess of it. That one in the middle should have been higher. So it would go like that. So, anyway, that was not important to our discussion. That was just to illustrate how important this function is in statistics. Very, very important. The normal distribution, the central limit theorem, incredibly important in statistics. So this function is very, very important in maths. Now the problem is that this function doesn't have a nice antiderivative. So its interval over which it's defined is, the entire real line, and it does not have a function capital F defined over the entire real line that differentiates to it. At least not in closed form. Now, what does that mean? So, closed form means a function that you can write down like this, for example, or like a polynomial function. It means that you cannot build it out of a finite number of algebraic operations, so things like plus, minus, times, division, or the functions that we accept in calculus. So exponentials we accept in calculus, they're a standard closed accepted form for calculus functions to have. And the trigonometric functions are also closed forms that are accepted in calculus, so sine, cos, they're accepted. You cannot build the antiderivative of this in closed form, i.e. you cannot use a finite number of trigonometric functions and adds and algebraic operations and get something that actually expresses the antiderivative of this. So for instance, an example of a closed form could be something really hideous. It could be something like e to the negative x cubed plus x squared plus e to the x in there, and then we could have all of that multiplied by sine of x, and then we could have it multiplied by a polynomial here, so x squared plus x cubed, and we could have it all over, let's say, cos of x squared plus x plus 1. That would be a closed form expression. It's built out of functions that are accepted in calculus. These are algebraic structures, x times x times x plus x times x. This is all algebraically defined. This is another function accepted in calculus. So this is a closed form calculus expression. You can prove that there is no such closed form. It's not easy, but you can prove that there is no such closed form expression in calculus that differentiates to this. So that is a problem. Instead, you need infinite expressions to describe the antiderivative of this. That is a problem because this is a function that we want to have a definition of the integral. The integral for under intervals of this is very important in probability theory, if we want to find out the probability that if something is normally distributed, that its value, that you get value between, let's say, x1 here and x2 here, we want this integral here. So we want this to be nicely formally defined. If we took this as our definition, this would kind of be excluded from that because it doesn't have this nice function capital F that is its antiderivative. So that is why this is a bad way of formally defining it. I mean, there's two reasons really. One, we'd actually have to prove that this does capture the concept of the area, but we could do that. And two, we would be excluding functions that don't have a nice antiderivative here. It's reliant on these functions having a nice antiderivative, which isn't the way that we want to go about defining integration. So that's why this is cancelled. We're going to now look at the way that we do actually define Riemann integration. So I've now erased all of that so that we can return to something sensible. So we want to look at the Darboux definition of the Riemann integral. Now to do this, we need to know the concepts of the upper Riemann sum and the lower Riemann sum. And to do that, we need to firstly look at the concept of a dissection of the interval AB. So this we will often abbreviate to D. So this is very intuitive. A dissection means to cut up. A dissection is a cut up, a way of cutting up this interval AB. And you can cut it up into a different number of pieces. So different dissections D will have a different number of pieces, and we'll call the number of pieces that it's cut up into little n, where little n is obviously going to be a positive integer, one of the counting numbers. So if I bring the interval AB out here, and I can show this to you. So let's say we're going to cut it up into 5 pieces, so n is going to be 5. So we can select the boundaries for those 5 pieces however we like. So I could put one, for instance, here, I could put one here, I could put one here, so we've now got 4 pieces, and I could put a final one there. So to make this dissection, to define this dissection, I just need to know where these bits, these cuts, are going to be. So you've cut the interval here, 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 and you've now cut it, dissected it into 5 pieces. So actually, the information that defines this is just where those cuts are going to be made. So we often define the dissection just as this finite sequence of places where you're going to make the cuts. And just for simplicity, we also include the endpoints in this sequence. So we often call A, we'll rename that x0. So that's going to be the 0th term in our finite sequence. And then it's going to be strictly less than the next cut, which is going to be called x1. So this is called x1, that's the first cut. And then that's going to be strictly less than x2, which is going to be that second cut, which is going to be strictly less than x3, which is that third cut, which is strictly less than x4, which is this fourth cut, which is strictly less than x5, which is just a relabeled up version of B. So therefore, the formal definition of what your dissection is it's this finite sequence x0, x1, x2, x3, x4, all the way up to x5. So it's a sequence of length 6 with 6 terms in it, where the first term and the last term are actually trivial. They're just the boundaries of our interval, and then it's the bits in between that are important because they're actually defining where these cuts are being made. So that would be a dissection into 5 pieces, and it therefore has 6 numbers in the sequence that defines it. Let me give you another example. So let's take a bigger dissection. So a dissection into, let's say, 10 pieces. So this is going to now have 11 terms in the sequence if we include the x0th term, which we do need to include, A, just for niceness. So we could do this again however you like. So you could make other dissections of number 5. I didn't have to make the cuts here. There are an infinite number of dissections where I've cut it into 5 different pieces, where I move where I'm going to put these cuts. I change what these numbers are. The requirement on them is these inequalities here, that the next term along in the sequence must be strictly less than the last. So that's really the requirement on this sequence in order for it to be a dissection, that the first term is going to be A, the last term is going to be B, and then the other terms in between need to be strictly increasing. So any sequence that satisfies those conditions, no matter how long it is, as long as it's finite length, is going to be a dissection of our interval AB. So if I take, therefore, a sequence x0, which is A, x1, x2, x3, all the way up to x10, which is B, this will be a dissection of this interval AB, where we're dissecting it into 10 parts, provided that for all of these, xi is strictly less than xi plus 1. As long as those criteria are met, that this is A, this is B, and then all the terms in the middle satisfy this, so for all I running from 0 to 9, this needs to be true, then this will correctly be a dissection, and I can translate it into a picture over here. So that will cut this into 10 different bits, and let me make sure I get this right. So far we've got 7 pieces, I think. Yes, 7, 8, 9, 10. There we go. Let me just count them and make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Excellent. So this again is x1 here, x2 here, x3 here, x4 here, x5 here, x6 here, x7, x8, x9, and then b is x10. Good. So that's the concept of a dissection of our closed interval AB. Now it is closely related to the concept of a partition, which we could call P of the interval AB. Now, when I was first taught Riemann integral, the Riemann integration topic, I was taught it as dissections, which is why I still prefer to call this concept a dissection, D. However, if you go to analysis textbooks, they don't often call it a dissection. Instead, they call this concept a partition instead. So it's far more common that you'll see this. However, because I was first taught it this way, it's the one that's stuck in my head, and it's the one I still prefer. So I'm going to follow on and teach it to you like that and talk about dissections throughout this video. However, be aware that most textbooks will instead refer to a partition of the interval AB rather than dissection. Now, the formality of this is slightly different because in a partition, they're capturing exactly the same concepts of cutting the interval up into pieces. It's just the technicality of how it's being captured is slightly different. So in a dissection, we think of it as we're going to store the information of where the cuts are in this sequence, like so, whereas in a partition, what you do to formally capture this concept is instead you define the partition. So actually, this is the formal definition of dissection. This thing, this sequence is the dissection. For a partition, the partition P is actually a set, and it's a set containing the chopped up intervals rather than the cuts. So if we want to capture the same cut up as this in the form of a partition, it would be you'd have the interval x0 to x1, x1 to x2, and then so on, x2 to x3, x3 to x4, and then all the way up to x4 to x5. And again, you'd have the same requirements on these cuts. You'd have the requirements that this holds true again, that xi is strictly less than xi plus 1 for all the i's that are relevant. So from I is equal to 0 right the way up to n minus 1. So it's just a slight, it's difference in semantics. You know, the formal way that we're capturing it is different between a partition and a dissection, but actually intuitively what they are capturing, the information, is utterly equivalent. So throughout this video I will talk about dissections because I prefer it just because it was the way I was first taught it, but be aware that in many other places, textbooks and indeed your lecturer at university might use the term partition instead, but they are capturing the exact same concept of cutting up your interval into little pieces.